I want you to take a second and just mentally transport yourself back to school.
Okay.
It's a hot afternoon. Maybe the ceiling fans are struggling a bit, and you're walking down the corridor towards the science wing.
I can picture it.
You turn into the biology lab, and immediately it hits you.
That smell.
Oh, I know exactly where you're going with this.
Number one, right? It's sharp, it's pungent, it sort of stings the back of your nose and sticks to your uniform for hours.
The classic biology practical experience, yes.
You look at the shelves,
Yeah.
and there are those glass jars with the yellowing liquid. Inside, there's a frog or an earthworm just floating there.
And it's been there forever.
Exactly. For 10 years, looking exactly the same. It hasn't rotted, it hasn't decayed, it's just frozen in time. That smell is the smell of Unit 8.
It is. That is the smell of formalin. And while it might trigger some, not so great memories of practical exams, what you're actually smelling is one of the most versatile chemical groups doing its job. Welcome back to the deep dive. Today, we're cracking open the NSERT textbooks again, specifically Unit 8, Topic 5. We are talking about the uses of aldehydes and ketones.
And I am really glad we're doing this specific topic today.
Oh, why is that?
Because usually when students study organic chemistry, they get so bogged down in the mechanics. Nucleophilic addition, the arrows moving, the sp2 hybridized carbons.
It feels like just drawing shapes, not doing science. It feels like geometry class.
Precisely. But this topic, the uses, this is where the rubber meets the road. This is the why do we care section.
Right.
We're going to connect those abstract structures to massive global industries. We're talking about medicines, the plastic switches on your wall, and yes, that dead frog in the biology lab.
So the mission for today is simple. We want to take this list of uses that students usually just mug up 5 minutes before the exam and turn it into something they actually understand.
We want to build a mental model. So when you see the chemical formula in the question paper, you don't just see letters. You see a function. You see a tool.
Okay, let's start at the most basic level. If I'm a class 12 student, I see a carbon double bonded to an oxygen. The carbonyl group. Why is this one bond so useful in the real world?
I want you to think of aldehydes and ketones as molecular tools.
Okay, molecular tools. I like that. Unpack it for me.
A tool has a specific shape and a specific function, right? A hammer hits things, a screwdriver turns things.
Sure.
These molecules are tools because of that carbonyl group.
Yeah.
It makes them highly reactive and highly polar.
So because they have this positive and negative and the polarity, and because they want to react with other things, they can do jobs that other molecules like alkanes just can't.
Exactly. Think about an alkane like methane. It's like a smooth, round rock. It's lazy, doesn't do much. But a carbonyl, that C double bond O is like a hook. It grabs onto things.
So let's use some analogies. If we look at the big players, formaldehyde, acetone, what kind of tools are they?
Let's look at the toolbox. First, you have formaldehyde. It's the smallest one. Think of this as your universal glue.
Glue.
It reacts to stitch things together. It binds molecules into big nets. That's why we use it to make resins and hard plastics.
Okay, so formaldehyde is the glue. What about acetone, the first ketone?
Acetone is your universal solvent. It's the cleaner. It washes things away, dissolves sticky messes, and then, this is the best part, it vanishes. It just evaporates.
The glue and the solvent. What about aromatic aldehydes, like benzaldehyde?
Those are your fragrance molecules. They are the tools that trigger our sense of smell. If you smell almonds or cinnamon or vanilla, you're smelling an aldehyde.
I want everyone listening to try and visualize this. Close your eyes for a second. Picture formaldehyde first. It's tiny, right? Just one carbon.
Very small.
Yeah.
HGHO. It's light, zipping around, very energetic.
So it's zipping around, looking for something to latch onto. That's the glue. Now picture acetone. It's a bit bigger. It's like a liquid that's sort of nervous. It wants to turn into a gas.
That's a great way to put it.
It grabs onto dirt or paint, dissolves it, breaks it apart, and then poof, it just floats away.
That is a great mental image. And what's really happening underneath all that comes down to 3 properties: reactivity, polarity, and volatility.
Okay, let's break those down just so we are clear on the technical terms.
Sure. First, reactivity. The carbon in the CO bond is electron deficient. It's hungry, so it's great for synthesis, for making new things.
Right.
Second is polarity. The oxygen pulls electrons, making the molecule a little magnet. This helps it dissolve things.
And the third one, volatility.
Volatility, especially for the small ones. The forces holding them together are weak. They want to escape into the air. That's why you can smell them.
So when a student asks, are these just random chemicals on a lab shelf? What's the answer?
I say that is a massive misunderstanding. Formaldehyde and acetone are two of the most produced organic chemicals on the planet. Billions of tons.
Billions. Wow.
They are the invisible pillars of the modern economy. Without them, you don't have your phone case, you don't have your car paint, nothing.
That really puts it into perspective. Now, to help lock this in, our source material uses a really interesting analogy with water.
Yes, this is a great way to understand their versatility. Think about how we use water. Water does many things, right?
Kills your car engine, dissolves salt, sustains life.
Exactly. The uses of aldehydes and ketones are just like that. Formaldehyde is a reactant building plastics, just like water can be a reactant.
And acetone is a solvent, like water-dissolving salt.
And glucose, which is a polyhydroxyaldehyde, is the fuel for biology, just like water sustains life.
That connects the dots so well, it's not a one-trick pony. But let me play devil's advocate. Why is this topic even in the syllabus? Why does the board exam care if the student knows that acetone dissolves paint?
It solves the so what problem.
Hmm.
You spend weeks learning about bond angles. The uses topic proves that without understanding that CO bond, we wouldn't have the modern world.
We wouldn't have hard plastics or pure medicines.
Or even understand our own metabolism.
You mentioned plastics. I saw the word bakelite in the notes. That sounds familiar.
It should. Historically, it is huge. Bakelite was the first fully synthetic plastic made from phenol and formaldehyde.
Oh, you mean those old electrical switches? The dark brown ones in older houses?
The very same one.
The ones that make that really loud, satisfying click-clack sound.
That is the one. That is Bakelite. Incredibly hard, heat-resistant, and electrical insulator. And it is pure aldehyde chemistry. It's just a giant net of phenol molecules.
Stitched together by formaldehyde, the glue.
Exactly. And think about acetone. It was critical in World War I for making smokeless gunpowder. The outcome of the war at one point depended on how much acetone could be produced.
Wow. Okay, so these molecules literally shaped history. Let's take our listeners on a little journey now, a mental movie.
Let's do it.
Listeners, close your eyes again. We are going to follow the life of two different molecules. Scene one, we are in a massive, hot chemical factory, pipes everywhere.
We start with methanol. It gets oxidized, heated up, and transformed into that sharp formaldehyde gas.
It travels through a pipe to a resin plant. It meets a solution of phenol. They react.
The formaldehyde starts grabbing the phenol rings, linking them up, tighter and tighter, like knitting a messy sweater.
The mixture is poured into a mold, it cools down, and it becomes that rock-hard, dark brown, solid bakelite. Decades later, someone flips that switch. Click.
A perfect example of reactivity creating a permanent structure, from a gas to a solid rock.
Now, scene two. We synthesize acetone. It sits in a tank. It's jittery. It has a low boiling point.
It wants to escape.
It gets bottled and sent to a cosmetic factory. Ends up in a small bottle of nail polish remover. You're at home. You open the bottle. Whoosh. That sweet chemical smell hits you.
Instantly.
You pour a little on a cotton ball. It feels cold on your skin.
Right, because it's evaporating so fast, taking heat with it.
You wipe it on your nail. The acetone attacks the paint, weasels its way in, and breaks its grip. The paint dissolves. And then within seconds, poof.
The acetone is gone, back in the air. Your nail is dry.
That journey relies entirely on polarity to dissolve the paint and volatility to leave your finger dry.
Exactly. If you used water, your finger would be wet for ages. Acetone does the job and leaves.
It's not magic, it's just molecular behavior at work. Let's circle back to the start. The dead frog in the jar. We said the smell is formalin, but why doesn't the frog rot?
It's doing something much more physical than just poisoning bacteria. It's actually changing the structure of the frog itself.
How?
Well, formaldehyde is an aldehyde. It loves to react with amino groups, the NH2 groups. And where do we find amino groups?
In proteins, amino acids.
Right. The frog is made of protein. The bacteria that want to eat the frog are made of protein. The formalin attacks those amino groups and creates these crosslinks.
Crosslinks, like little bridges.
Exactly like that. Tiny bridges made of CH2 groups connecting different protein chains together. It literally stitches the proteins together, locks them in place.
So the bacteria can't eat the protein because it's chemically locked.
Precisely. The CO reactivity literally freezes biology in time.
That is slightly terrifying, but also very cool. Freezing biology in time. Okay, let's shift to something more high-tech. Pharmaceuticals and acetone. I don't want nail polish remover in my medicine.
No, you definitely don't.
Yeah.
But you need it to make the medicine pure. Imagine you've made a drug, say paracetamol. It's mixed with some leftover gunk. You need to clean it.
So you wash it.
You do. You dissolve the dirty mixture in a solvent like acetone. Now your drug is floating in the liquid. You filter out the solid dirt. Now you just have drug plus acetone.
But you need the powder, not a liquid.
And here is the key. Acetone has a boiling point of just 56 degrees Celsius.
That's really low. Water is 100.
Exactly. So you gently warm it, the acetone evaporates very easily, and it leaves behind pure, dry medicine crystals. No residue.
Oh.
If you used water, the heat needed might destroy the drug itself.
I see. So acetone is the perfect wash and dry cycle because it washes effectively but leaves quickly and gently.
It's the gentle touch, indispensable in labs.
Here is a counterintuitive example from the notes. Formaldehyde HCHO is so simple. It seems too simple to be this important.
You might think that, but actually its simplicity is its power.
How so?
Because it is so small, it can fit anywhere. It can wiggle into tight spaces between large molecules to create those crosslinks. And because it's simple, it's cheap to make. That's why billions of tons are used. Simple structure, massive economic value.
It's the Lego brick of the chemical world. The smallest piece is often the most useful.
That is a fantastic analogy.
Okay, we're getting closer to the end. We need to make sure our Class 12 listeners are ready for the board exam. We have a list of clarity lines.
Let's do this differently. I'll give you the chemical context. You give me the tieback, the why, or the application.
Okay, put me on the spot. I'm ready.
All right. Line 1, formaldehyde regarding polymers.
Okay. Formaldehyde is used to synthesize bakelite, a phenol formaldehyde resin. Tieback is. It's used in electrical switches because it's a hard, heat-resistant plastic.
Full marks. Line 2, acetone, its primary role.
Acetone is a key industrial solvent. Tieback, used for paints and nail polish removers due to its high polarity and volatility.
Correct. Don't forget to mention both properties, polarity and volatility. Line 3, formalin.
Formalin is 40% aqueous formaldehyde. Tieback, used as a preservative for biological specimens. Why? Because it cross-links proteins.
Key phrase, cross-links proteins. Perfect. Line 4, drug synthesis.
Aldehydes and ketones are intermediates in drug synthesis. Tieback, because the CEO group is highly reactive to nucleophiles.
Good. Line 5, aromatic aldehydes. Benzaldehyde, vanillin.
Used in perfumes and flavorings. Tieback, because of their distinctive pleasant scents.
And finally, line 6, biology. Glucose.
Glucose is a naturally occurring polyhydroxyaldehyde. Tieback. It is the primary energy source for living organisms.
Perfect. If you can articulate those 6 points, you've covered most of what you'll be asked.
Brilliant. Okay, let's wrap this up with a short summary.
Let's do it.
Today we learned that aldehydes and ketones are molecular tools driven by that reactive CO double bond.
We saw that formaldehyde is the glue, small and reactive, stitching together things like bakelite and frog proteins.
And acetone is the solvent, polar enough to wash dirty drugs, but volatile enough to vanish without a trace.
We visualize the journey from factory to your home. These molecules are everywhere.
So the final takeaway. When you walk into the exam hall, don't just see HCHO. Smell the formalin. Hear the click of the switch. Remember, these molecules are doing heavy lifting in the real world.
Well put.
Before we sign off, we always like to leave you with a provocative thought, something to chew on.
We spent a lot of time talking about acetone as an industrial solvent in a bottle. But did you know your body produces ketones, chemically, very similar to acetone right inside you?
Wait, really? Like, right now?
If you skipped lunch, yes.
Mm.
When you are fasting or on a low-carb diet, your body runs out of glucose, the aldehyde. So it switches gears. It starts breaking down fats and producing ketones to fuel your brain.
So ketones aren't just paint thinner.
They're emergency high-octane fuel for your brain.
So the difference between an aldehyde, glucose, and a ketone fuel determines if I'm hungry or burning fat.
Exactly. Chemistry isn't just in the lab. It is literally determining your metabolism right now. Why does the body switch to ketones? It's efficient energy. Something to think about next time you feel hungry.
That is wild. Thank you so much for joining us on this deep dive into Unit 8. Good luck with your studies, and we will see you in the next one.
Happy studying.